And then over here, if you forward backwards, if you accidentally press this, it just blocks it out. Just press it again.
Thank you.
And then I share.
Thank you.
You're welcome. All right. We can start like 1 minute early. Everybody should be here. Okay. So our next speaker is Amrutaa Vibho from Norwich University. Go ahead.
Thank you, Dr. Grant. Can everyone hear me? Online?
Yes, should be able to.
So this is going to be very different from what the talks have been today. I am not by any means a PhD, a grad student, even a graduate of college. I'm just here because Dr. Brand and Dr. Haas agreed to have me here and taught me a few things last year that I'm carrying forward this year. Good afternoon, everyone. My name is Amrutaa Vibho. I am a student of Norwich University, which is a military college in Vermont. One of my co-cadets is here. He's also from my university. So how this works is we study during the day and train during the night, train in the morning, stuff like that. I'm going to be speaking about my very first research project that ended up getting published. And if you remember from Dr. Brand's talk, there are some people that focus on machine learning applications in the field of fundamental relativity, cosmology, stuff like that. I'm one of those people. Dark matter subhalo interpretations using machine learning focuses on applying applying machine learning on the Fermi-LAT catalog, which is released by NASA called Space Flight Center. Those are gamma ray observations with the Fermi-LAT telescope, and I'm trying to see if we can map out possible dark matter correlations. How this is relevant to the Einstein toolkit, I will talk. A little bit about me. I'm from India. I am a student of physics and math, and I study chemistry and mechanical engineering at minor. This actually is a very recent photo of me down in Houston, the Mission Control Center, because I'm interviewing to be in the next class of astronauts. I don't know why I applied, just for fun. Let's see what happens. That's my chemistry research right there. This is research I do with the Vermont Space Ground Consortium on hyperspectral imagery of nanoparticles and using them to make a portable, essentially, water treatment system for the International Space Station. My main research that I want to do as a graduate student would be high energy astrophysics, which is why I'm here. That's the paper that ended up being published. So when I was graduating from high school, it was COVID year. Obviously, I actually got into UIUC, and I was supposed to go to UIUC for aerospace engineering. Then I ended up being able to go to COVID. Started doing research with students from the University of Chicago through the Horizon Academic Research Program. And they were teaching me applications of machine learning and sort of left me on my own after that. So I found interesting topics and an uninteresting paper on an application of machine learning on the Fermi-LAT catalog years before, which is what I started doing with that year's incremental catalog with Portman. The idea is that according to the lambda cold dark matter model, the matter energy equivalence, we are trying to model through n-body simulations, cold dark matter, dark energy, stuff like that. How interesting would it be to see if gamma rays are actually emitted from dark matter sources? Because we don't know what dark matter is. We don't have any equation state. We don't have what candidates they are. The idea behind it is, so we have, of course, positive confirmation that dark matter doesn't exist because the universe is expanding and there is more matter in the universe than is observed. In 1933, Fritz Zwicky actually, as most of us know, released his paper on the redshift of extragalactic nebulae that we observe more matter than we can observe with electromagnetism. So that interacts optically. And so the Fermi-LAT catalog records gamma ray sources from outside the Milky Way, nearly extragalactic and galactic sources. And most of them are associated sources, meaning their sources are known as on the right side. But this particular research focuses on building a dark matter subhalo set using pulsar data, globular clusters, and associated clusters. So according to lambda CDM, there are theories that deeply interacting massive particles or WIMPs and massive compact scale objects controls fall in the range of dark matter annihilation. So that flux falls in that range. 70 electron volts for this particular instrument from that catalog. So that gives us hope of trying to compare the energy spectrum of these sources with the unassociated sources using machine learning, learning complex patterns, and seeing if our model classifies these unassociated sources as possible dark matter. That's what I did. Why machine learning? Because it can uncover patterns that are not otherwise apparent. Can it have its faults? Yes. Which is where numerical relativity and what I'm going forward with. So I use multi-layer perceptron, which is a neural network, an artificial intelligence architecture, and support vector machines, which are Bayesian, which is why I asked the question earlier on Bayesian methods analysis. And the false positive, that's my false positive. As you can see, it's pretty decent for the most part. So on the Fermi-LAT catalog's fourth increment, there were 5,788 sources that were associated with a known gamma ray source, 1,667 unassociated. That's a big number. That's not good. So I basically chose the ones that are above 10 degrees of galactic, or almost extragalactic. Out of those, I could classify 30 using my model as potential dark matter candidates that have the flux density within this dark matter annihilation range and the gamma rays correspond. This is the data projection. Challenges. It's a very big claim. Taking a catalog using machine learning, claiming I know what dark matter is, or I found dark matter today. What I'm trying to do is I could get the annihilation cross section of these candidates that I identified, but the process is more complicated than my undergraduate brain. What I can possibly do is use LIGO data. So between the fourth increment, which was my first research of the Fermi-LAT, the fifth one, which was released later in 2023, December 2023, some of the sources that my model positively identified were moved to laser dark. That is not very good for my research. But my now advisor and I started looking in the direction of what if these are not self-annihilating dark matter structures. There are other theories that explore possibilities of dark matter being something else and not a particle nature. That's what LIGO. Primordial black holes could possibly be dark matter is a stipulation, has been for a while, especially since LIGO's first observation. So last year, I embarked on this journey. Googled black hole, LIGO, machine learning. Dr. Haas is making on. Dr. Haas and Dr. Eliu, who work at Argonne National Lab. He works at Argonne National Lab. They work at the gravity group doing simulations of highly eccentric black holes. Emailed them saying, I'm an undergraduate student. I did this. I don't know what to do. He said, come to RIT. We have this conference. So I met Dr. Brandt and Dr. Haas last year and realized that I could use numerical relativity to simulate primordial black holes. Parameter estimate using a catalog of sorts that I would get, then try to apply it to my dark matter catalog and see if there is a difference or it's impact. Now, of course, that's more difficult than I can imagine or imagine. So this is the research that I'm going off of. Right now, I have a catalog using these parameters and hyperparameters that I generated using AstroPy and Python mostly. My first step is to try to use the Einstein toolkit to simulate some of the things that I got using Python, which is why I'm here today. And I've been trying to ask and take help from Dr. Haas and students at NCSA and RIT to do this. My next step was to try to study the companion. The lambda CDM, I did start on the CDM, I wanted to study lambda. This is my advisor, Dr. John Saxon. We are trying to study the dark energy model using bulk viscosity as an explanation for dark. So his research believes that the negative pressure that is created by dark energy could also be contributed to by bulk viscosity, which they published And what he's looking at with me is the effect of shear viscosity that is possibly contributing to the perturbations of the particle. We use something called the cosmic linear anisotropy solving system. It's a C++ based code that solves for Einstein equations. And my job this year is try to implement a module, like you spoke about modularization. I'm trying to modularize particular part on shear viscosity, how it affects these graphs that we got from the previous research on bulk viscosity. If it matches up with what we have here. I don't expect to be able to answer a lot of your questions because I'm here because I'm excited about what I'm presenting, what I'm researching. Hopefully, you would have some input for me on what I could do in the future. This is all I have. Thank you for having me. Any inputs, any questions?
I don't understand exactly what you're trying to do, but I'm trying to understand, trying to correlate two things, dark matter and some phenomena.
Dark matter and primordial black holes, because we
You have to
don't-
repeat the question.
Sorry. Okay. So the question was, if I'm trying to correlate dark matter and something else, how I started off was trying to figure out if dark matter comes from gamma ray sources, mostly pulsar light, because they emit gamma rays, and their gamma ray density, flux density falls within the dark matter analysis range of 20 to 70. So when we started off with that, we found out that there is a good chance that the candidates we're looking at are not annihilating dark matter. So not gamma rays or pulsars. It could be primordial black holes.
So what's this machine learning and for correlation study?
Sorry?
What's the difference between machine learning and just a correlation study?
The question was, what's the difference between machine learning and using the correlation study? I would argue using machine learning, so there's something called transfer learning that I'm trying to use to transfer the effects of training my model on known sources to when I change the input to unknown sources. Now that would help me decipher between like I could transfer the same model between my gamma ray source catalog and my primordial black hole catalog. I would argue it is more transferable and more modular. I can add to it without modifying the code structure.
That's just correlation analysis.
I can see that. I guess correlation analysis because this is what I chose, but I wanted to work with.
Understand that.
Any other questions? So did you find any new blob that you could identify that no one has identified before?
There are four
Four.
in my paper, which I do not have one with you. But those four, I don't have it right now, but on my paper in the future work section, I have included that those four fall in the X-ray catalog of Chandra X-ray also.
And they were determined to be black holes?
They were determined to be pulsars,
Pulsars.
but we don't know with confidence. So they were in the DS9 error region of the
Okay.
Chandra X-ray catalog. So they could possibly have X-ray counterparts, and that's what we're going to do. So
Okay.
I did.
All right, any other questions? Okay, I guess not. Thank the speaker
Thank you.
again. That's not great. Correct.
You're the boss.
I'm the